Welcome! In this session, we'll explore an interesting problem titled Cousins in Binary Tree. Together, we'll analyze the problem, break it down into manageable pieces, and work through potential approaches to solve it. Let's dive in. In this problem, you are tasked with determining whether two nodes in a binary tree are cousins. To do this, you're given the root of a binary tree, which contains unique integer values, and two specific integers, x and y. The goal is to return true if the nodes corresponding to these values are cousins and false otherwise. Now, what does it mean for two nodes to be cousins? First, they must be at the same depth in the tree, meaning they are on the same level. Second, they must have different parents, meaning they are not siblings. The input consists of the binary tree itself, represented by nodes with properties such as val for the node's integer value, and left and right references for its children. Additionally, you'll be provided with the two integer values, x and y, whose relationship you need to evaluate. The output is a Boolean value indicating whether the nodes x and y fulfill the conditions to be cousins. Let's take a look at the first example. Here, the input binary tree is represented as 1, 2, 3, 4, and we are checking the relationship between nodes with values x equals 4 and y equals 3. When visualized, the tree has 1 as the root, with 2 and 3 as its left and right children, respectively, and 4 as the left child of node 2. In this case, the function returns false. This is because the nodes 4 and 3 do not meet the criteria for being cousins. Specifically, they are not at the same depth in the tree. Node 4 is located one level deeper than node 3, which immediately disqualifies them from being cousins. Breaking this example down further, node 4 is at depth 2 in the tree, and its parent is node 2. On the other hand, node 3 is at depth 1, with node 1 as its parent. Since these two nodes are not at the same depth, they fail the first condition required to be cousins. Now, consider a second example where the input tree is represented as 1, 2, 3, null, 4, null, 5, and we are checking for x equals 5 and y equals 4. In this case, the function returns true. Here, the tree can be visualized with node 1 as the root, nodes 2 and 3 as its children, node 4 as the right child of node 2, and node 5 as the right child of node 3. Let's delve into why these nodes meet the criteria for being cousins. In this second example, node 4 is at depth 2 in the tree, with node 2 as its parent. Similarly, node 5 is also at depth 2, but its parent is node 3. Since 4 and 5 are at the same depth and have different parents, they meet both conditions for being cousins. This is why the function returns true in this case. Now, for the third example, the input tree is represented as 1, 2, 3, null, 4, and we are checking if nodes x equals 2 and y equals 3 are cousins. The tree can be visualized with node 1 as the root, and nodes 2 and 3 as its left and right children, respectively. Node 4 is the right child of node 2. In this case, the function will return false, and here's why. For this third example, node 2 is at depth 1, and its parent is node 1. Similarly, node 3 is also at depth 1, and its parent is also node 1. While these nodes are at the same depth, they fail the second condition for being cousins because they share the same parent. This makes them siblings rather than cousins. Finally, let's consider some constraints and edge cases. The tree will have between 2 and 100 nodes, and all node values are unique integers between 1 and 100. It's also guaranteed that x and y will always exist in the tree and will not be the same value. Edge cases include small trees with only 2 nodes, where x and y would be siblings, unbalanced trees, and scenarios where x and y are either at different depths or share the same parent. These constraints ensure that the problem remains well-defined and solvable within the given limits. To determine whether two nodes, x and y, in a binary tree are cousins, we considered multiple approaches. The first is the brute force approach. Here, the idea is to traverse the tree multiple times to gather the depth and parent information for both x and y. For instance, we could perform a DFS or BFS to find the depth of x, then traverse again to find the depth of y. After that, we compare their depths and ensure their parents are different. However, this approach is inefficient because it involves multiple traversals of the tree, resulting in a time complexity of n squared, in the worst case. Its space complexity is h, where h is the height of the tree, due to the stack or queue required for traversal. The drawback here is the repeated work, which makes it unsuitable for large trees. To address this inefficiency, we also considered an optimized single traversal approach. This method uses either BFS or DFS to collect all necessary information about X and Y in just one pass through the tree. By tracking both depth and parent information during the traversal, we can determine if X and Y are cousins once they are both found. This approach is much more efficient, with a time complexity of O, N, and a space complexity of O, H, for DFS or O, W, for BFS, where W is the maximum width of the tree. The optimized single traversal approach has clear advantages. It eliminates redundant computations, focusing on efficiency and simplicity. Another variation of this is the alternative BFS approach with level tracking. Here, we use BFS to explicitly process nodes level by level and gather parent information. Specifically, for each level, we check if both X and Y exist and ensure their parents are different. If one node is found but not the other, we can immediately conclude that they are not cousins. This method is also efficient, with a time complexity of O, N, and a space complexity of O, W. Its step-by-step processing makes it especially easy to implement and well-suited for problems that require level-order analysis. Overall, both optimized methods offer significant improvements over the brute force approach, making them better candidates for solving this problem effectively. Among the approaches considered, we chose the optimized single traversal approach using BFS. While DFS is also a viable option, BFS is particularly intuitive for problems that involve comparisons at the same depth. With BFS, we process nodes level by level, which makes it straightforward to compare X and Y as soon as they are encountered. Both BFS and DFS allow us to gather the depth and parent information in one traversal, but BFS avoids the complexity of backtracking and provides a clear level-based perspective. The efficiency of O, N, time complexity is achieved by avoiding redundant traversals, which is critical for larger trees. On the other hand, the brute force approach, while conceptually simple, falls short due to its inefficiency, as it requires multiple passes through the tree. BFS does come with a trade-off, as it requires a queue to store nodes at each level, which can increase memory usage if the tree is wide. However, this memory usage is generally manageable in practice, making BFS a well-balanced choice for this problem. Although DFS is similarly efficient, its depth-first nature makes it less intuitive for level-based checks, which is why we lean toward BFS as the preferred strategy. By employing BFS, we can efficiently gather the depth and parent information for nodes X and Y in a single traversal. This method allows us to verify the cousin conditions, whether the nodes are at the same depth and have different parents, once both nodes are located. The clarity of this approach lies in its level-by-level processing, making it easy to organize and compare nodes as we go. This strategy balances efficiency and simplicity, ensuring optimal performance for both small and large binary trees. By avoiding redundant computations and leveraging the natural structure of BFS, we achieve a solution that is both intuitive and effective for solving the problem of determining cousin nodes in a binary tree. To determine if two nodes, X and Y, in a binary tree are cousins, we need to ensure two conditions are met. First, they must be at the same depth in the tree, and second, they must have different parents. To solve this, we'll follow a systematic approach. The goal is to find the depth and parent of both nodes X and Y. Using this information, we can verify the conditions for cousinhood. To achieve this, we'll rely on breadth-first search, or BFS, as our traversal method. BFS is particularly useful here because it processes nodes level by level, making it easy to track the depth of nodes. Let's initialize BFS using a queue. Each element in the queue will be a tuple containing the current node and its parent. For the root node, the parent will be set to none. We start by enqueuing the root node along with its parent, which is none. From here, we perform a level-order traversal of the tree. For each node, we dequeue the first element and check whether the current node matches either X or Y. If it does, we store its depth and parent information. If both X and Y have been found, we can terminate the traversal early. Otherwise, we enqueue the left and right children of the current node, setting the current node as their parent. Once the traversal is complete, we use the stored depth and parent information to evaluate the two cousin conditions: first, whether X and Y have the same depth, and second, whether they have different parents. If both conditions are true, we return true. Otherwise, we return false. Using BFS ensures that our implementation is straightforward and efficient for this problem. Additionally, it's worth noting that the algorithm can terminate early as soon as both x and y are found, which helps optimize performance. Some edge cases also need to be considered. For example, if either x or y is not present in the tree, the algorithm should return false. Similarly, if either x or y is the root of the tree, they cannot have cousins since the root has no parent. From a data structure's perspective, we use a queue to implement BFS, with each element storing a tuple of the current node and its parent. We also use variables to store the depth and parent information for x and y. In terms of complexity, the time complexity is O, n, where n is the number of nodes in the tree, since each node is visited once. The space complexity is O, w, where w is the maximum width of the tree, as this accounts for the space required by the BFS queue. Let's now look at the pseudocode to understand the implementation more concretely. The pseudocode begins by handling an edge case. If the root of the tree is none, the function immediately returns false. We then initialize a queue for the BFS traversal, starting with the root node and its parent as none. The variables depth_x and depth_y are initialized to -1, and parent_x and parent_y are set to none. These will store the depth and parent information for x and y as we traverse the tree. We also initialize a variable depth to keep track of the current level during the BFS. The while loop processes each level of the tree. For each node in the current level, we dequeue it and check whether it matches x or y. If it does, we record its depth and parent. We then enqueue the left and right children, along with the current node as their parent. Once all nodes in the current level are processed, we increment the depth variable to reflect the next level. To optimize performance, the loop can terminate early if both x and y have already been found. After exiting the loop, we check the two cousin conditions. First, we compare the depths of x and y to ensure they are the same. Second, we verify that their parents are different. If both conditions are satisfied, we return true, indicating that x and y are cousins. Otherwise, we return false. To see the algorithm in action, let's consider an example. Imagine a binary tree where the root node is 1, with children 2 and 3. Node 2 has a left child 4, and node 3 has a right child 5. If the inputs are x equals 4 and y equals 5, the algorithm will start BFS from the root, processing nodes level by level. At the first level, the algorithm processes the root node, 1. At the second level, it processes nodes 2 and 3, storing their parent as 1. At the third level, it processes nodes 4 and 5, storing their parents as 2 and 3, respectively. At this point, the depths of nodes 4 and 5 are the same, but their parents are different. Therefore, the algorithm returns true, confirming that 4 and 5 are cousins. This example highlights how BFS efficiently determines cousin relationships by leveraging depth and parent information while traversing the tree. This is a solution to LeetCode problem number 993, cousins in binary tree. The goal is to determine if two nodes, x and y, in a binary tree are cousins. Nodes are considered cousins if they are at the same depth in the tree but have different parents. ####line by line explanation. 1. The method isCousins is defined. It takes the root of the binary tree and the target nodes x and y as inputs. 2. A helper function, find_depth_n_parent, is defined within isCousins. This function is responsible for finding the depth and parent of a node with the given value, val. It takes 4 arguments: the current node, the value to search for, val, the current depth, and the parent of the current node. If the current node is none, it returns none, indicating the value wasn't found in this subtree. If the current node's value matches the target value, it returns a tuple containing the depth and parent of the node. Otherwise, it recursively searches the left and right subtrees. If the value is found in the left subtree, the result is returned immediately. If not, the right subtree is searched. 3. The find_depth_n_parent function is called twice, once for x and once for y. This retrieves the depth and parent information for both nodes. Finally, the method checks whether x and y satisfy the conditions for being cousins. Their depths must be equal. Their parents must be different. 5. The result of the comparison is returned as a Boolean value. ### complexity analysis. The time complexity is O(n), where n is the number of nodes in the binary tree. This is because we may need to traverse the entire tree to find x and y. The space complexity is O(h), where h is the height of the tree. This accounts for the recursive call stack during the depth-first search. This solution is efficient and handles all edge cases, including when x or y does not exist in the tree, or when the tree is empty. Here, we start by defining our Java solution to determine if two nodes in a binary tree are cousins. The main method, isCousins, takes the root of the tree and the two values, x and y, as input. The first step is to gather information about these two nodes by using a helper method called findDepthAndParent. This method will return an array containing two pieces of information, the depth of the node and the value of its parent. For both x and y, we call this helper method, passing the root, the target value, an initial depth of 0, and a null parent since the root has no parent. After retrieving the information for both nodes, we check if they are cousins. This is done by verifying that they have the same depth but different parents. If both conditions are true, we return true, otherwise, we return false. Now let's take a closer look at the helper method. The helper method findDepthAndParent is a recursive function designed to traverse the tree and locate the node with the specified value. It takes the current node, the target value, the current depth, and the parent node as its parameters. If the current node is null, indicating we've reached the end of a path, it returns null. If the current node matches the target value, it returns an array containing the current depth and the parent's value. For the recursive search, it first explores the left subtree, increasing the depth by 1 and passing the current node as the parent. If the left subtree search returns a result, it's immediately returned. Otherwise, the search continues in the right subtree. This ensures the method finds and returns the depth and parent information for the target node. Finally, we define the treenode class, which represents the structure of the binary tree nodes. Each node contains an integer value, a reference to its left child, and a reference to its right child. Multiple constructors are provided to initialize nodes with or without child references, ensuring flexibility in tree creation. The goal of this problem is to determine if two nodes in a binary tree are cousins. Remember, two nodes are considered cousins if they are at the same depth but have different parents. To solve this, we'll analyze the tree structure and use a helper function to find the depth and parent of each target node. For instance, in the example where the tree is 1, 2, 3, 4, and the target nodes are x equals 4 and y equals 3, the tree looks like this: 1 is the root, with 2 and 3 as its children, and 4 is the left child of 2. To check if 4 and 3 are cousins, we start by focusing on node 4. We'll call the helper function to find both its depth and its parent, beginning at the root. After starting at the root, node 1, we traverse left to node 2. Node 2 is at depth 1, and its parent is node 1. Continuing, we traverse left again to node 4, which is found at depth 2, with node 2 as its parent. This gives us the result, depth 2, parent 2, for node 4. Next, we perform the same process for node 3. Starting again at the root, we move right to node 3, which is located at depth 1, with node 1 as its parent. This results in depth 1, parent 1, for node 3. Comparing these results, we observe that the depths of nodes 4 and 3 are not the same. Node 4 is at depth 2, while node 3 is at depth 1. Since they are not at the same depth, they cannot be cousins. Therefore, the output is false. Now let's consider another example where the tree is 1, 2, 3, 4, 5, 6, 7, and the target nodes are x equals 4 and y equals 6. In this tree, node 1 is the root, with 2 and 3 as its children. Nodes 4 and 5 are children of node 2, while nodes 6 and 7 are children of node 3. To determine if nodes 4 and 6 are cousins, we start by finding information for node 4. From the root, we traverse left to node 2, which is at depth 1 with node 1 as its parent. Then, we go left again to node 4, which is at depth 2, with node 2 as its parent. This gives us depth 2, parent 2, for node 4. For node 6, we start at the root, traverse right to node 3 at depth 1, then go left to node 6 at depth 2, with node 3 as its parent. This results in depth 2, parent 3, for node 6. Comparing these values, we see that nodes 4 and 6 have the same depth, but different parents. Node 4's parent is 2, and node 6's parent is 3. Since both conditions for being cousins are satisfied, the output is true. Finally, let's examine a case where the nodes share the same parent. In the tree 1, 2, 3, 4, 5, with x equals 4 and y equals 5, the structure shows node 1 is the root, with 2 and 3 as its children. Nodes 4 and 5 are both children of node 2. To find information for node 4, we start at the root, traverse left to node 2 at depth 1, and then go left again to node 4 at depth 2, with node 2 as its parent. This gives us depth 2, parent 2, for node 4. For node 5, starting from the root, we traverse left to node 2 and then go right to node 5, which is also at depth 2 with node 2 as its parent. This results in depth 2, parent 2, for node 5. Comparing these results, we see that while the depths are the same, the parents are also the same. Both nodes share parent 2. Since cousins must have different parents, the output here is false. This highlights that the helper function, which retrieves depth and parent information, is crucial for accurately determining cousin relationships. The algorithm efficiently solves the problem in n time, where n is the total number of nodes in the tree. The time complexity of this solution is primarily determined by the recursive function find_depth_n_parent, which uses a depth-first search or DFS approach to traverse the binary tree. This function explores each node of the tree exactly once, and in the worst case, it will traverse the entire tree, making the time complexity n, where n is the total number of nodes. Since we call this function twice, once for each target node, x and y, you might think the complexity doubles. However, big O notation simplifies this to n, as constants are ignored. Now, if we consider the best-case scenario, where x and y are located near the root, the recursion might terminate early after visiting only a small portion of the tree. Despite this, in big O terms, we still consider the worst-case scenario of n, since the entire tree could need traversal. Similarly, in the average case, the function would explore roughly half the tree for each of the two values, but again, due to the nature of DFS, the overall time complexity remains n. Therefore, whether we're looking at the best, average, or worst case, the time complexity for this approach is consistently n. To further solidify this, let's consider a mathematical perspective. During a DFS traversal, each node in the binary tree is visited exactly once, and at each node, the operations performed are constant, or 1. Thus, the total work done during one traversal is proportional to the number of nodes, or n. Since we call find_depth_n_parent twice, this results in 2 n, which simplifies to n. Now, shifting our focus to space complexity, it is primarily dictated by the depth of the recursive call stack used during DFS. In the worst case, the recursion depth aligns with the height of the tree. For a balanced binary tree, the height is log n, resulting in log n space for the stack. However, in the case of a skewed binary tree where each node has only one child, the height becomes n, leading to n space usage for the recursion stack. Besides the recursive stack, other variables like x_depth, x_parent, y_depth, and y_parent require only constant space, which is 1. This means the overall space complexity is dominated by the recursion stack. To summarize the overall space complexity, we can see that it varies depending on the structure of the tree. For a balanced tree, the recursion depth is log n, so the space complexity is log n. However, for a skewed tree, where the nodes form essentially a straight line, the recursion depth reaches n, resulting in a space complexity of n. When comparing this solution to a naive approach, the advantages become clear. A brute force method might involve traversing the entire tree to create a map of depths and parent nodes for all values. This would require n time for the traversal and an additional n space for storing this map. In contrast, the current approach calculates the depth and parent information directly during the DFS traversal, avoiding the need for extra storage. This makes the current solution significantly more space efficient. Additionally, because the operations are performed in place during the traversal, the solution is both simpler and more efficient. In summary, the time complexity of this solution is n for all cases, as the entire tree may need to be traversed in the worst scenario. The space complexity depends on the tree structure, O log n, for a balanced tree due to the recursion depth, and O n, for a skewed tree, where the recursion depth equals the number of nodes. Overall, this approach is optimal and more efficient than a naive solution, particularly in terms of space usage, as it avoids additional storage requirements. By leveraging an efficient DFS traversal, the solution ensures both simplicity and optimal performance, making it a robust choice for solving the problem. When working on the problem of determining if two nodes in a binary tree are cousins, there are some common mistakes to watch out for. First, it's easy to confuse the sibling check with the cousin check. Remember, cousins must have the same depth but different parents, so you need to ensure both conditions are met to avoid mistakenly identifying siblings as cousins. Another common pitfall is neglecting edge cases. For example, the tree might be empty, one or both nodes might not exist, or the nodes might even be the same. These scenarios can lead to incorrect results unless explicitly handled. Additionally, inefficient traversal is a frequent issue. If you're traversing the tree multiple times to gather parent and depth information, you could end up with an O(n)² solution. Instead, aim for a single traversal with an O(n) complexity by collecting data for both nodes in one pass. Finally, ensure your depth calculation is accurate by incrementing the depth only as you move down each level of the tree. Misplacing this step can lead to incorrect results. Another area where errors can occur is in implementing your traversal method, such as BFS or DFS. If you don't stop traversing once both nodes are found, you'll end up doing unnecessary work. To optimize, gather the required information as soon as possible and exit early. Now, from an interview perspective, there are several insights to keep in mind. Always clarify constraints, such as whether the nodes are guaranteed to exist in the tree. This affects how you validate the inputs. Space complexity is another important discussion point. BFS typically uses O(n) space, while DFS can be optimized to O(h), where h is the height of the tree. Be prepared to explain this trade-off. Additionally, discussing edge cases, like nodes being at different depths or the tree being skewed, demonstrates a strong understanding of the problem. Finally, emphasize how parent tracking is done, as it's a crucial part of the solution and shows that you understand the core mechanics of the problem. To deepen your understanding of this problem, it's helpful to explore related problems that sharpen similar skills. For instance, LeetCode 104, which focuses on finding the maximum depth of a binary tree, is great for practicing tree traversal and depth calculation. Similarly, LeetCode 111 helps you work on minimum depth calculations but with different constraints. LeetCode 863 is particularly relevant, as it involves finding nodes at specific depths, which aligns closely with the logic of cousin checks. Lastly, LeetCode 572 tests your ability to traverse and compare subtrees, reinforcing your tree manipulation skills. Beyond related problems, let's consider alternative approaches. Using BFS with a queue is a straightforward way to ensure level-order traversal, and it's particularly useful when the tree is balanced. However, it does require O(n) space. On the other hand, DFS with recursion is more space-efficient for skewed trees, as it only requires O(h) space. This makes it a better choice when the height of the tree is small, but it requires careful management of the recursive stack. Another powerful approach involves using a hash map to track both the parent and depth information for nodes. This method allows for quick lookups, which is especially useful if you need to verify multiple cousin relationships in the same tree. The trade-off is that it requires additional space, specifically O(n), for the hash map, but the efficiency in querying makes it ideal for scenarios where repeated checks are necessary. By understanding when and how to use these different strategies, you can tailor your solution to the specifics of the problem and the constraints given, ensuring both correctness and optimal performance. Thank you for watching. In this session, we explored the cousins in binary tree problem, summarized key approaches, and discussed important takeaways. If you enjoyed this, be sure to like, subscribe, and stay tuned for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!